Okay, Chapter 3, Question 157. We have a compound of molar mass 229 grams per mole. Put that up here. Equals 229 grams per mole. What else we have? Contains only carbon, hydrogen. So carbon, hydrogen, iodine, sulfur. Analysis shows that a sample of the compound contains 6 times as much carbon as hydrogen by mass. So that means 6 grams of carbon, you're going to see 1 gram of hydrogen. And we are asked to calculate the molecular formula of the compound. Okay, so I think these questions seem a lot tougher than they are. It sort of seems a little overwhelming at first, like you got nowhere near enough material to start with. I think these are sort of a little bit of a conceptual battle to get going in the first place. So we're gonna start by writing out what exactly a molecular formula is. So we're gonna write down all of our constituent species here, as in all of the element species that make this compound up, and I'm putting variables down here to stand for whatever their stoichiometric coefficients are going to be. So that there's our molecular formula in the rough. So this is equal to saying that W times the formula weight of carbon, plus X times the formula weight of hydrogen, and blah, 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 and blah, 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 the rest of these things is going to be equal to the formula weight of the whole molecule. That's what this here means. So we're going to write that out in full form so you can see exactly what I mean here. So if I go W, and I'm going to actually write out what these numbers are here, 0.1 grams per mole. That's the formula weight for carbon. X times formula weight of hydrogen, that's 1.008 grams per mole. All right, Y times, what is iodine? 126.90. That is a big element. Per mole. And last is Z times sulfur is 32.07 grams per mole. And this whole expression here is equal to 229 grams per mole. All right, so we've got a common factor of grams per mole in each of these terms. We're going to divide that out, rewrite all of these things just as the numerical values of the formula weights as coefficients for the variables. And that's going to make it a lot, easier to, well, not really easier to handle, but it's a lot easier for me to write. But I always feel better when these things look cleaner. Oh yeah, I feel better already. 690 plus 3207Z equals 229. All right, now we're off to the races. So when you start one of these questions, there's typically going to be some low-hanging fruit in the form of some elemental species that has a molecular weight that's so large that 2 of them can't be present in the molecule and still leave weight for some of the other species. And we have that in this case in iodine. What I mean when I'm saying that is that if they mention that carbon, hydrogen, sulfur are present, that means that W, X, and Z have to equal at least 1. None of these numbers are never going to be 0, right? And they're also going to be whole integer values. There aren't going to be decimals or fractions or anything like that. And the formula weight for iodine is so large that we can't fit 2 of them in there. 2 times the formula weight for iodine is bigger than the entire formula weight. Right? That's, what is it? 2 times 126.9. This is what? 253.8. Right? Don't even need the calculator. Obviously, it's bigger. Yeah. So we know that we can't have more than one atom of iodine present in the molecule. So we know that Y is equal to 0. Or Y is equal to 1. Sorry, not equal to 0. Good grief. So I got to write that up here. And we're going to put together our formula bit by bit. So I'll write C and I'll leave W blank. H, X blank. I is done. So we'll leave that as that and put S right next to it. Okay, and let's keep going. And actually, as we continue, we're gonna take these, we're gonna simplify these out of there and keep making this easier and easier and easier and easier to write. All right, so I'm going to make myself some space here and do just that. Okay, so we got 12.01W, 1.008X plus 32.07Z, and this is equal to 229 minus the molecular weight of iodine, right, times whatever Y is, right? And because Y is 1 in this case, right, multiplied by 1 means 229 minus 126.9 gives us 102. 102.1. All right, now let's we'll keep going. Okay, we're going to use this relationship here to get to get us a little further. So 6 grams of carbon per 1 gram of hydrogen. So let's sort of express that in these terms. That means that this ratio here divided by 1.008x. Don't sweat these uncommon variables. We're going to fix that in a second. This is equal to 6. That's what it means to have 6 times more of this up top than this on the bottom, right? And we got grams in both, so we can do this sort of thing. I'm gonna write this in terms of a common variable x. All right, so we're gonna use that to solve for hydrogen, and so this is gonna become 6x over x. That's also equal to 6, which means it's equal to that. Like if they're both equal to the same thing, then they're equal to each other. So now our formula becomes this. Becomes 6x plus x plus 32.07z equals 102.1. And we can collect like here for 7x. 2.07z equals 102.1. All right. So now we're ready to do another one. So we could see here that we're going to have to divide this by 7. So like either we're dividing this by some multiple of 7 in order to leave a result that is divisible evenly by 32.07, which is difficult, or we subtract some multiple of 32.07 to leave something that's divisible by 7. And that's quite a bit easier to do. So we're going to do exactly that. What I'm saying in this case, like we need to find Z such that 102.1 minus 32.07Z equals something divisible by 7. Some multiple of 7. And we're going to do this by guess and check. All right, so here we go. Here's our first one. We're going to assume that Z is equal to 1. All right, actually, you know what? I'm going to make this explicit. Assume Z equals 1. All right, and that means that we would have 7x equals 102.1 minus 32.07 times 1. All right, and this is equal to 70.03. All right. We got lucky on the first guess. This is going to work. You see, this is not exact, right? This is not exact. This is good enough. For sure, that's good enough. All right, so we're going to use z is equal to 1. And we're going to put that up here too. Z equal to 1. Don't have to change anything because this is at the end there. Okay, and that also gives us x equal to 70.03 over 7, which is equal to 10. Right? Close enough, right? Again, like these all have to be even integers. There's no decimals in these things, right? So you just round all these things to your heart's content. Okay, so if x equals 10, we're going to put that up here. Right? And we'll put it in the formula, and at this point it's all over but the fat lady singing. Okay, so now we're gonna use this term here. Well, this one here, and we're gonna solve it for w. So 6x equals x, or sorry, 6x over x equals 6, and we're gonna write this 6x term in terms of w. All right, so 12.01 w, right, divided by, right, that's the value of x in there, and this equals 6, so w is equal to 6 times 10 times that, so that's 60 point, well, no idea, let's write it like that. And then we're going to divide that by the 12.01 here. And hopefully that's going to give us something even. And that is going to be 5. Again, more or less, right? But close is good enough in this case. All right, I've run out of room to write this one in, so I'm just going to write this straight in here. And that there is our molecular formula.